Okay, good morning. So here we are, Tuesday, January 18th. So let's get started. You are proceeding through Chapter 2, basically, right? So let's take a look at Chapter 2. There's a number of topics that I sort of introduce into Chapter 2. Well, not sort of, that I actually introduce. And so, running through this, clearly on exam 1, I'm not going to ask you a whole lot of things from Chapter 2. The idea of Chapter 2 is that it sets the foundation for understanding, certainly why do you have to study statistics. And then in particular, I spent just a little bit of time introducing you to the justification for why you want to learn statistical software like R, and in particular why we chose R for you to learn. I run you through a little bit about the history of statistics, and we introduce the concept of experimental design. So you at this point in your career at Chaminade, you've done hopefully quite a few experiments, ranging from experiments that have been designed for you, and now you should be in the process of actually designing and carrying out experiments. You do that a little bit in Biology 308 with me, and you certainly do that with Dr. Wright and Dr. Cogbill and Dr. Hank in their courses, particularly in the labs, right? And so it's an interesting point of view that if you kind of embrace statistics, it really helps with the idea of how to design an experiment. Not just in terms of things like sample size and whatnot, but actually provides the foundation for understanding why you design experiments the way you do. Remember, the basic part about an experiment is that it's a test of a hypothesis. And so the better your hypothesis is at making predictions, the more clean your experiment will be. And the easier, if you will, to interpret and make inferences about the data and reach conclusions. And so integral to experimental design, and also the foundation for using statistics, is understanding the scientific method. Now, practicing scientists, don't necessarily operate every single waking moment on the cusp of the scientific method, right? They don't step 1, step 2, step 3, but what in fact they do is that it's a core philosophy about approaching how to understand the way nature works. And so a big part of scientific method is critical thinking skills, of course, and learning how to think about data. So statistical reasoning is a really big, important part about being a good scientist. Okay, so more practical terms, what you should be doing now is, of course, you should have installed R and R Commander by now. You may have some kinks, some things to work out, but if you haven't started, you're behind. Get going. Make contact with me if you're running into problems. Well, I have a lot of help in our book, as well as in our workbook, as well, finally, in the Canvas site about how to work with and install R and stuff. I understand that there can be some hesitation about the error messages that you're receiving, or you think you're getting error messages and whatnot. So look, just because we're not in class doesn't mean stuff's not happening. Of course you need to get installed R and R Commander, or if you can't, you need to contact me. So with that said, then you should be working in Mike's workbook for Biostatistics. There's a section called A Quick Look at R and R Commander, and it has 10 parts. And so we'll start it. The first part, of course, is to get R installed. The second part then starts introducing you to entering commands into R, and so on and so forth. Now, in terms of the statistics course itself, what you should be doing now is you should be looking at and trying homework 1. Again, that's in Mike's workbook for Biostatistics. This is a word problem, and it's about identifying assumptions in an analysis, right? And it doesn't require you to use R or any other software. This is a, critical thinking exercise, okay? And then you'll see the deadlines on it, but I would expect you then to submit your answers into Canvas in the link at Homework 1. So let's take a quick look at the, the workbook. I haven't really shown you that before. So that's at mikeworkbook.letgen.org. There are links off Canvas and, of course, from your main textbook. But if you kind of cruise through here, this is the content that we have. So I mentioned the quick look at R. So the first one again is to take a look at installing R. And there's not much there because it's referring you to the 2 chapters in Mike's Biostatistics book. Okay? I'll also introduce you there. I've mentioned that the simplest way to do this semester is to get R installed on your PC or your Mac operating system computer. But if you don't own a computer, instead have a tablet, or it'll be interesting, but if you're going to try to work your way through the course using just your smartphone, there is a way to do it. It's not a simple way. The learning curve is a little clunky, but the advantage of this is if you go with the running R in the cloud, okay, like GoCalc or Google's Colaboratory, you can take this anywhere, and you develop notebooks, and then you can run code in the cloud, and you don't have to be, at your computer. You can do it through your smartphone or whatnot. And, again, mostly I provide you with the code, right? This isn't a coding course. While I introduce you to coding, the idea is that I provide you code and then you just simply adapt the code to your own particular situation. Okay, so continuing our journey through the workbook, all right, here are your homeworks for the semester. So magically numbered 1 through 10. Covers basically the 10 core concepts of statistics that we're going to be doing this semester. Okay? And then I provide you with answers to some or part of the homework as we go through it. Okay? So that's the workbook. All right? And coming back here is Mike's Biostatistics book, right? Your main textbook. Okay, there's the 20 chapters in the table of contents, and we are working our way through chapter 2. Just as a way, I give you sort of a topic list up at the top in this blue box, and then at the bottom of the page I provide you links to the different sections within the chapter. I'll say this is always a work in progress. I've been updating this like a crazy person behind the scenes, and so some of the links don't work, and you can earn extra credit if you tell me the links are broken. But more specifically, don't just tell me, hey, I found a link that was broken. Use good troubleshooting skills. Tell me what page you were on and what you were trying to link. All right? And sometimes a screenshot's a good way to do that. So we'll post a reminder about how to do troubleshooting when we talked about computers. But that's where we're at, right? So we're in chapter 2. Okay. And here are the things that we're going to go over today. So one of the advantages of being online is we're doing a recording here, and so you can kind of sit back and come and go, but I'm going to try to plow through basically a good hour's worth of material here. So off we go. All right. So first order of business, I kind of want to sell you a little bit about this statistics stuff. Some of you probably have some, hesitancy about it because it's like, oh, this is math, and I'm not comfortable doing math. I did okay, but I just don't really like it. And it's like, I appreciate that, but it's today, meaning, the times that we're living in, you don't have to do the math so much to understand statistics. You just need to know what the statistical procedures are asking of the data, and you need to have some sense of how the interpretation follows conditions that have to hold in order to ask the questions, right? And so it isn't really about, doing the math. It's understanding why you're pressing the buttons on the computer asking for a particular statistical function. And so it doesn't mean that you shouldn't learn the math, but the thing is that this is an introductory course. And so what I'm choosing to do is to teach you, I hope, how to sort of navigate through the logic, how to navigate through the interpretation, how to deal with the various output in relation to the experiments that you've designed. You're a biologist first, or those of you who are going to go on to in medicine, whether it's in public health or as medical doctors or what have you, you're going to be faced with all kinds of data, and other people will have run the statistics for you, but you'll need to be able to understand how to interpret those results. What you don't want to have is a situation in which you have to trust somebody that says, well, this is what it means. You should, at the end of this semester, be able to tell people what it means, and you should be able to listen to others and their conclusions and go, okay, that makes sense, or no, there's something missing there. Or you'll be able to ask the key questions about how they analyze the data so that you can trust the assumptions, trust the conclusions, and whatnot. Okay, so why biostatistics? As we talked about last week, statistics is the science of collecting, organizing, and interpreting data, and biostats refers to use of statistics in biology. So look, if you're a biologist, and to some extent I include medicine as a discipline of biology. Obviously, we are biological beings, and so therefore, when things go wrong with us, there are biological explanations for what's going on. And so the explanations are based on observation, so the collecting of and interpreting of data, right? So what statistics does is set a series of principles that allow you to identify a well-designed experiment, proceed to how do you analyze the results of the experiment, and then finally how to interpret the results in reference to what's going on with the biology. So about, I guess it's about 10 years now, we redesigned the curriculum at Chaminade so that it explicitly includes an undergraduate course in biology for statistics. Okay, so can you do biology without statistics? No. No. Even if you think you're doing biology without doing statistics, the underlying logic is invoking statistical procedures. So for example, in molecular biology, you may be looking at the, an image from a gel, and you're looking for the presence, absence of a particular band in the gel. Well, welcome to doing statistics. That's called a categorical data type, presence, absence, so binomial. You can answer, is the band there, yes or no? So that's a data type. And there's a whole host of ways that you would then go about interpreting that result. Clearly, an experiment is not a single gel, right? You would do the gel over and over and over again because you want to confirm that band always appears. If it appears only some of the time, right, that becomes, you have to interpret that. And so that some of the time to all of the time, that's again a particular kind of observation, and interpreting it requires statistical inference. So you're doing statistics whether you recognize it or not. Okay? I just did a real quick, look at the number of times in a biology-based, reference database, PubMed, and the word statistics is mentioned basically about 1 million times, which is probably an underestimate of the number of times it actually is, because it's a little bit like breathing. You don't necessarily mention breathing in your papers. They don't write statistics, even though that's what they're doing. Okay, so I I would also suggest that it's pretty hard to get through being an educated person without some sense of how to do statistics. And there's nothing clearer than, our daily reports on the COVID-19 pandemic. So, they report what they're calling case numbers, right? How many cases were reported by the Department of Health. We're in the Omicron phase of the pandemic. And so in Hawaii, we're talking about every day they're reporting thousands of new cases. And so this is an example of epidemiology. We're in the middle of a pandemic, and the subdiscipline of medicine that deals with communicable diseases like the COVID-19 is epidemiology, and underlying epidemiology is a whole bunch of statistical procedures that we'll call biostatistics. All right, I already mentioned sort of the idea of molecular biology sometimes doesn't seem like it's doing statistics, but of course it has a statistical perspective. So for example, I talked about presence-absence data in a gel looking for a particular band, but then there's the more basic stuff. You're often told, look, you need to do at least 3 runs of this, 3 trials. And so where does this 3 come through? And it's like, well, that's because it's a basic number that you need in order to carry out a particular calculation, calculating the standard deviation. Okay, so the other part about it is that even if you're ignoring statistics beyond, sort of calculating the average and the standard deviation, there's a whole underlying set of issues about how you interpret your results. So for example, the multiple comparisons problem. So it's not unusual to do an experiment that maybe has multiple outcomes. And so therefore, there's a tendency to ask multiple questions of the same data set. And it's like, well, but the data set provides different outcomes, so it's not just recovery from surgery, but there's, how soon are they back on their feet? There's any number of things that you might ask from an experiment when you're comparing 2 different procedures, for example. And so the tendency is to sort of milk the data to try to answer as many questions as possible. And so anyway, once we work into this tendency to sort of overwork data is what's called a multiple comparison problem. And it means that you're going to end up making errors in judgment, not because you don't know what you're doing, but because the data being used multiple ways is not independent, nor was it necessarily collected specifically to test each one of those different questions. And so this brings into question how well you can interpret all of those answers, given it's only one set of data. Okay, so I'm kind of going off on that. That doesn't show up until basically chapter 12, so we've got some time. All right, I'm just sort of pointing out that even if you don't think you're doing statistics, you are doing statistics. Your conclusions depend on the assumptions that go into your inferences, and statistics helps you identify those assumptions and whether you're in good shape or not. And then finally, and this is something clearly molecular biology does a very good job, is talking about the difference between, you have to do replication in science, right? You don't just get an answer once and go, I've cured cancer. You'd want to do it again, right? And over and over and over again. And so those are called replicates. And so how the replicates are counted, whether they are independent organisms, so biological replicates, or if you've measured the same organism over and over again, those are replicates too, but they're what we'll call technical replicates. And this is 2 different kinds of replications, and they give you different answers about your data. Okay, so what do we mean? No, I mean that you're doing statistics even if you don't think you are. Okay. Additional justification, medical doctors' jobs, graduate programs require a year or more of statistical training now. You get better at doing experiments if you learn statistics. Okay, where do they work? Well, basically everywhere. How's that? Okay, so let's move on to justifying why I'm having you install R. Well, one justification is that you'll use it in other courses on campus. So psychology department, education department, behavioral science, criminal justice, they all use R software. Business tends to use SPSS, but some of them are also learning to apply R. So I mentioned, the first week that we're going to be using R and R Commander. I've mentioned running Jupyter notebooks so R in the cloud using Jupyter notebooks. CoCalc is a site that allows you to do that. But again, you're not required. Again, this isn't a course on coding, but you'll benefit if you load R onto your own computer. And the main reason is that, let's say you lose your Wi-Fi connection. Well, there goes. You can't run R in the cloud, can you? All right. So having it on your own computer means that you're a self-contained, lean, mean, statistical machine. Sorry, old 1980s joke. Okay. All right. So continuing, so we want you to install R. Got it. All right. So why R and not other software? So in Chapter 2, I go to some length to defend installing R versus trying to do statistics in Excel or other spreadsheet programs. And the main reason for not using a spreadsheet program is that it wasn't designed to run sophisticated statistics. If you learn how to code, you can make Excel or Google Sheets or just about any spreadsheet program do some really very sophisticated statistical procedures. But you have to know how to code, or you have to be willing to buy additional software that plugs into those programs to gain that function. And the other is, it's not easy to learn how to do statistics in a spreadsheet program. Okay, you have to learn a series of commands. You have to learn how to write some basic functions. So R, while it seems intimidating at first, R is designed to do statistical analysis. And so once you kind of get used to the blank sheet when it gets started, R is much easier in the long run to do statistics than trying to force a spreadsheet program to do it. And so then let's be even more practical about why R is a good thing to do. It's free, all right? And so it's thousands of people the world over contribute to the R project. There's a core group of people that sort of run the show, and they're all volunteers. So that doesn't necessarily justify you should choose R. Well, they're volunteers, but the volunteers these are people who do statistics and data analysis for a living. They're academians, they're business people throughout the world. And of course, part of academia is you need to publish, and so for a number of people, writing a new statistical procedure and providing the R code to run it, that's a publication, right? So there's a justification for them to learn R. And the flip side also is that it's open source. So some of you know about the open source movement. It's been around since basically the beginning of computers, which the idea is that you should share your code. You shouldn't make it a business model. Now, Microsoft and Apple and others in the early 80s basically pushed back on that model. And so we've had, ever since, we certainly have an enormous commercial aspect to coding and software. But the advantage of the open source, in particular in statistics, is that you can actually see how the thing's coded, right? You can look at the code and you can figure out whether in fact it does what it claims to do. And so there are software that do statistics, so SAS and SPSS, Minitab and whatnot, and those are commercial versions, and they're closed. You're not allowed to look at the code. So doing good science is you want to know everything about what you're throwing into the test tube, or, and so while we buy kits frequently, we need to validate the kits that they actually measure what we claim. And so it's no different with statistical software. You want to be able to understand how it does its calculations. And so it's R itself, and unfortunately it's just called R. So when you do a Google search and you do R, that's not going to work. And so if you do R project or R core team or R statistics, that will usually get you pretty close to it. But it's widely respected and widely used across different professional fields. Lots of people, as you start searching out on the internet, write about how to do different kinds of analysis in R. So it's all available on the internet. R is really good at making publishable quality graphics. It's not always really easy to generate a great graph, but the procedures are there, and one of the things to do is to just sort of try to do different things and see if you can generate these pretty pictures. And so I've got some examples in chapter. So over 18,000, 700 packages, and the packages are the new algorithms or new ways of looking at old statistics or new statistical procedures. And so you have to buy those packages if you subscribe to SPSS. So SPSS gives you a base package, and then if you want additional capabilities, you have to purchase them. So R provides cutting edge new statistical procedures routinely. And on the other hand, that's kind of complicated, right? How could you possibly, well, of course you don't need all 19,000 packages. So we use a different sets of packages, and throughout the semester I have you add to your base installation of R with new packages as we need them. Okay? All right. So diverse kinds of statistical tests, absolutely. In fact, in many cases, the SPSS in SAS and whatnot will lag behind by quite a period of time when there are new statistical procedures. Well, one example is a thing called a distance correlation. So this is a relatively new measure of association between two variables. And the statistical measure was first described, I think, in like 2009, 2010, and it was implemented in R right away, but it still isn't available in things like Minitab or SPSS. Okay, and then the final part is that I already mentioned this. It's like, well, I already use Excel, you might think, or I've been using Excel to do statistics in other courses. So look, to do the kinds of statistical tests, once we get past chapters 3 and, well, yeah, basically chapter 3 is kind of it, all right? Excel doesn't do the other statistical tests very well. You can get it to do linear regression. You can get it to do analysis of variance. But only certain kinds of experimental designs, and again, the commands themselves are quite complicated. So the learning curve to do statistics in Excel is significant. R is not easy either, but the end result is that you get a much, much more flexible software package to do statistics. Excel can only do it in a couple of different ways without you being able to add in costly packages to improve its function. Okay. So anyway, those are my reasons for adopting R. I mentioned last week that by the end of the semester you'll have enough experience to R that you can put yourself out in the gig economy to do basic data analysis, certainly data entry, right? And so the more you do, I'm not saying, for example, that you shouldn't learn how to use Excel or Google Sheets. There's a reason that spreadsheets are so popular. They're really useful for managing data, and you can using things called pivot tables, right? They're very useful for making some quick descriptive statistical interpretations. How many in this group? How many in this group? Well, what if this question and that question? So Google Sheets and Excel and other spreadsheets are pretty good for that. If you elect to investigate Jupyter notebooks a little bit, okay, if you learn how to run them, it's easy enough to generate some pretty complex analysis pipelines through these notebooks. And so this is the beginning of data analysis, right, and data analytics. And then finally R. And so this is just a count at this gig economy freelance database. You can sign yourself up, 5RR, and these are some of the skills that people listed when they're talking about data analysis. Okay, so let's move over to a little history. I encourage you to read for no reason at all. So if you're reading about politics, good. If you're reading about the pandemic, even better. If you want to support your education, then it's good to read within your field. So you're taking these various courses, and so there are often, popular books that would help you understand your that course even better. And so there's maybe less popular books about statistics. I suppose that's not surprising because, again, as soon as you say statistics, people's eyes kind of roll. But it's far more interesting than you think, and there are some books out there. You can pick and choose some things through various websites. If you just say brief history of statistics, you'll probably find all kinds of things. But this book, written, 20 years ago now, is a really good introduction by a historian of science to the history of statistics. And so statistics per se has been around with us a long time. Basically, as soon as civilizations came to be and strong central governments, the governments wanted to keep track of their population. So that's a type of statistics. How many people are within my nation? And so that's from that the idea of censuses were developed, right? You periodically will count the number of heads in a country. That's a statistic, the number of heads, the number of people, right? And so what we think about statistics, though, is about asking questions about data and experiments, and that didn't really come about until much later in the game, basically in the 1800s. That the core concept of statistics is about probability, and that's been around for quite a while. And so this book talks about all of those basic ideas about the history of statistics. Okay, so as I mentioned, statistics in the olden days is about state information, state numbers. Okay, it's not just a European and British thing. It goes back to, and probably was present in Incan and Mayan times as well. Okay, so statistics has two meanings. It's a classified fact representing conditions of a people and state. All right, so statistics can mean a description or an estimate. And then statistics also means, so this is a contextual difference, right? It means you're asking questions about populations from samples. Statistical inference itself only goes back into the early 20th century. Okay. There we go. So inference then is the probability that an event will occur. We're asking that question, how likely, when we have two drugs that we think affect A1C levels, or is it, yeah, A1C levels, and we want to see if there's a difference, that effectiveness, that difference is in the event. Another question, given a person is 99 years old today, how likely will they live until tomorrow? It's a pretty direct question, right? But that's a statistical question because you're talking about an individual, but the individual belongs to a population of individuals who all share the same characteristics. So you look to see, in the historical record, what's the probability of an individual who has these characteristics that they will live an additional day or an additional year, right? A fairly famous risk analysis is the idea of, is it safer to travel by airplane, commercial airplane, or by car? So when you're going through my book, you'll see I do an analysis on that. And so the event, of course, is injury or death. Mortality rate, that's the event. And you could be comparing cities that have different characteristics in terms of pollution. Another, of course, scenario where we're talking about how likely is an event. So right now, living through this pandemic, the question is, how likely is the virus to spread from individual to individual? So the statistic that epidemiologists come up with is called a reproduction number. And given different parts about the environment in which the virus is trying to spread, so how many people are vaccinated, how many people are immune to the virus. So of course immunity comes from vaccination, or it could come from prior infection, right? And so the reproduction number gives you some sense of how easy the virus is to spread from individual to individual. The reproduction number, if it's less than 1, then the virus isn't going to spread. If it's greater than 1, it's going to spread. And then it's a question of how large is the number. And it's a challenging number statistic to estimate, but the original variant, the reproduction number is about 2, depending on where you are. It's greater than 1, but at about 2. The Delta variant, so that was like the third wave, I think. And so reproductive number was about 5. And the variant that we're experiencing now, the reproductive number is 7. So this allows us to model how rapidly the virus spreads from individual to individual, and is used in public health to sort of assess what are our steps that we need to take. So these are all events. Remember, we have a very narrow definition in everyday language what an event is, but an event is an outcome. And statistics is about assigning a probability value to that. How likely will that outcome happen? How likely is that event to occur? Okay, so let's run you through a description of a typical kind of experiment that you might try at a party or something, and it's probably by the end of the story you'll be asked to leave the party because it's kind of a boring question, right? I would just simply submit this. If you're a scientist, this is a fascinating question. This is the kind of stuff that we talk about. So rumor has it that Ronald Fisher, who is a big name in statistics, he's long since passed away, but he's the inventor of a number of statistical procedures that we still use. And so sort of the rumor has it is he was at a academic party and they got to talking about another person, and it was a woman who either the wife or another professor, I forget the original story. Basically she says something along the lines, I can taste the difference when milk or tea is poured first into the cup. So in other words, you put the milk in the cup first and then you add tea, or the other option is you put tea in and then you add the milk. And so her claim is, well, yeah, of course I can tell the difference. And so of course the men in the room, they go, oh no, you can't do that. It's not possible. Once you mix them, there's no difference, right? Okay, so how would you test that? So basically he came up with the idea of, look, well, let's give her 4 cups of tea. In the tea, 4 of the cups, the tea is added first, and then the milk's added. And in the other 4 cups, milk's added first, followed by the tea. Then he randomized the order in which the cups were presented to the woman. And she sipped at them one at a time, and then declared tea first or milk first, right? Okay, so success is to guess the number of times out of 4, right? How many times do you get corrected? The whole experiment, there's 8, so she had 8 possible different, cups to sip from. And by the way, she got all 8 cups correct. So you can figure out what's the likelihood of that outcome simply by chance alone. Thinking about a coin flip, right? So you know what a coin is, right? Of course you do. So heads or tails, and so you flip the coin. Ooh, I've got a demo. So heads, oops, heads, tails, heads. Okay, that was painful. Let's try not to do that again. If I throw the coin onto the table, okay, right now it appears heads. So if I flip it again, what's the chance that it'll show up heads again? Well, 50%. And if you do it over and over again, if you get a string of heads, 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 your sense about fairness starts to waver about whether or not this is a fair coin. But you can actually calculate how likely it is in 5 tosses of the coin, how likely is it to get 5 heads in a row. So that's what he did, is he figured out every possible combination of her guessing correctly, and that would range from, well, for 8, you might not guess at all, any of them. So how likely is that? So that's 1 in 70 times, and so on and so forth. You use a combination calculation, and that little exclamation point, if you remember, that's an algorithm call. That means that you multiply 8 times 7 times 6 times 5 times 4, etc., and then divide it by 4 times 3 times 2 times 1, right? And you get 70. Okay. So you understand sort of the reasoning here. You design an experiment and you apply certain procedures so that you can rule out chance as the most likely explanation. So the key part of his experiment was he randomized the order in which the cups were given to her. It doesn't say, but obviously she would need to have been blind to whether it was milk first or tea first, right? She couldn't know in advance that she was receiving something in order for it to be a fair test. Okay, so from Fisher we got the notion of what's called the Null Hypothesis, which is a general statement that basically says whatever differences I see, it's just due to chance. And this is one of the big leaps that you need to go through. Just because you get a certain result doesn't mean you've actually cured cancer. The reason that you got that result can be simply because of the sampling procedures that you did. So you would need to repeat the experiment over and over again. And even if you get the same results, that doesn't necessarily mean you've cured cancer, right? There's additional assumptions. But the point being is that what you're testing is the idea that whatever difference that you see, you can rule out chance alone as being the explanation for the difference. All right, so kind of what's evolved since Fisher developed the idea of this null hypothesis is a combination of things that are called basically the frequentist approach, or the null hypothesis significance testing approach. So students of Fisher, came up with basically, yes, there's the null hypothesis, and then there's also the alternate or alternative hypothesis. So the null hypothesis is a specific statement that there's no difference between two things or two groups, and the alternate is, well, there is a difference. And so the idea then is to calculate what are called error rates that are associated with those two hypotheses. And so error rates are better known as probabilities. How likely are the data explained. You see this difference if the null hypothesis is true. Okay, so we'll do a little test here. So these are called Zener cards, and I don't know if you know about extrasensory perception, right? So this is the idea that some people are thought to be able to read other people's minds, for example, so good psychics, right? And so over the years, people have tried to test claims of extrasensory perception. And because you're working with humans, it turns out, you know, these experiments are not as easy to do as you think. And so go ahead and take a moment and pick a card. So what card do you think is going to show up next? Is it a circle, a plus, wavy lines, a square, or a star? Made your selection? Okay. So I had selected a plus. And so I've done this, you know, over the years. And, you know, because you guys are somewhere else, I can't actually query you this very easily. But, you know, over the years, most people have chosen waves. Fewer people have chosen pluses, right? So if they chose plus, is that evidence that they have extrasensory perception? Well, you know, again, there were 5 cards, so you have a 20% chance of being right. So we would, of course, do it over and over again, and we would ask how many times does a person guess the correct card, and even if they do, is that evidence of ESP? But you get the sense. How do we test these different hypotheses, right? We got to figure out experiments that allow you to rule out other interpretations, and that's where tests of ESP are quite hard. Okay. Some other things about the history of statistics. Unfortunately, a number of the creators of statistical procedures were themselves what we would call eugenicists. Eugenicism is the idea of basically controlling which humans are allowed to have kids, right? And so this was a progressive, liberal, scientific position towards social and political policy making at the turn of from the 19th to the 20th century. So a number of the statisticians of the time, so Francis Galton and Carl Pearson and Ronald Fisher, were all, if not members, or in some cases they were leaders of the eugenicist movement. And so it's a kind of an interesting philosophical point of view, right? So I hope you appreciate that controlling human breeding, who has kids and who doesn't, is at the very least unethical. And we are a society of laws, and the laws are based on ethical considerations when they're at their best. And so clearly being a eugenicist is counter to our sensibilities. It's certainly counter to the law of the United States now. So the interesting philosophical point is, so these were some, from our perspective, some pretty bad thinking people. So should you use the fruits of their genesis for why they came up with these statistical procedures? Now, the answer is that certainly society has moved on, and yes, absolutely, they incorporate all of these statistical procedures because they've decided that the algorithms are neutral with respect to this. And that's actually, that there's some debate about whether that's true or not. But something to consider. The origins of statistics has a pretty shady past. Okay. Let's move on a little bit about experimental design. So there's 2 types of studies. There's observational studies and there are experimental studies. So experimental studies allow you to identify, well, you have an outcome, right, that you're interested in, and you manipulate the situation in which that outcome comes about. in its best form, it allows you to ascribe cause to the outcome. Why did it happen? Well, we manipulated the situation. We controlled who received the treatment, and so therefore the difference can be attributed to, well, the new drug that we designed. Observational studies are different in the sense that the treatments have already happened. Nature put individuals into the different groups. Okay, and so clearly you can observe the outcomes of what nature's doing, but you can't really ascribe cause and effect. You're not doing a control group, for example. And so it's a much more difficult road to establishing cause and effect. Observational studies can tell you about how there's a correlation, so therefore it generates a hypothesis that you can then design an experiment for to test. We'll spend a whole chapter on experimental design, and experimental design considerations are sprinkled throughout our book. So a little bit about cause and effect. Hopefully you know what I mean by that, right? Cause and effect refers to an explanation about the relationship between two events or objects or things. In biology, a long time ago, a famous evolutionary biologist added into the philosophical discussion about cause and effect and scientific method by saying that our explanations in biology have really kind of two different types of explanations. At the one level, you can maybe call it the proximate, the mechanism. How did this different phenotype come to be? So you can talk about the biochemical pathway, you can talk about developmental history, gene expression profiles at different stages in development. How do cells become differentiated? How? Explain the mechanism. But then there's another level of explanation is, well, why is it that way? Why couldn't it have been some other way? And so ultimate explanations in biology come from evolution. You should appreciate, though, that the other level of ultimate explanation is, of course, saying, well, God did it. It's that way because God did it. So this is where, in the ultimate explanations, that sometimes biologists and religious philosophers, et cetera, will come to some collision about interpreting why something is. But we can all agree about mechanism, and so the mechanism clearly falls into, when you're thinking about the scientific method, in particular, that's where the scientific method is really good at, is discussing how things work. Doesn't mean ultimate level explanations don't follow the scientific method, but they may be a little bit more challenging to meet all the conditions of what we think of the scientific method. Okay, I'm not going to read through all of this, but I sort of, in the book, put on one side, a formulation of the statistical interpretation of the scientific method. And so we will return to this, but this is the workflow on the right-hand side, kind of working your way through an experiment, right? You develop a hypothesis. In the frequentist approach, which is basically the approach that we're going to show you, the classical statistical approach, you also then coin the alternate hypothesis. You state your predictions from the null and alternate hypotheses, and if they don't have clear predictive ability, that means your hypothesis isn't very good, so you'd want to rework that. But given that you have a set of hypotheses, that's how you work to design a good experiment, or how you go about collecting your observations. Collect your data, do some data management to make the data suitable for analysis, and then you analyze the data, right? Given the results from the analysis, you interpret. And finally, you evaluate the predictions from the null and alternate hypothesis. Excuse me. Okay, so characteristics of a good experiment. Look, it should be interesting. If you're asking a boring question or a question that's been well worked out, yeah, not so much. So, one of my challenges when I'm designing experiments for you guys in our science courses is that there's this idea that if we have a well worked out answer, so you do the experiment, we know what you're going to get, well, that's the way to teach you how to do science. And there's a point to that. Those are called demonstrations. And it's easy to assess them because it's like, this is the results, and so therefore this is the conclusion you should have gotten, and how come you're saying something else, right? So it's easy to, at least in principle, it's easy to grade those, to evaluate those. And there's certainly a place for that. But I tend to run my lab classes in which the experiments may not be that complicated, but we don't really know what the answer is ahead of time. And so we can work on the same teaching things. How, given the data, well, what were your hypotheses? And do the results confirm or refute your hypotheses, right? Okay, so anyway, interesting question is an essential part of doing, good scientists and doing a good experiment. And then making your hypothesis something that makes clear predictions is an essential part of designing an experiment. You got to have the hypothesis first, okay? You don't start collecting data and sort of see where it falls and then say, oh, I think this is what's going on. Another key element to doing experiment, and not everybody appreciates this, but you need to incorporate randomization into your experimental design. So we'll talk at some length about what that means, but here briefly, imagine that you want to study the effectiveness of a new drug on lowering A1C levels. So A1C is a marker for type 2 diabetes. And once you get over 7%, that basically means you're well on your way to full-blown type 2 diabetes. Okay? And so you have a new pharmaceutical therapy, a drug, treatment, that is claimed to reduce A1C levels. So how would you test that claim? Well, one way to do it would be to recruit every single person who has an A1C level of like 5% or 6%, and then see then over time, does it reduce? And it's like, you could do that. It would cost you billions of dollars to actually do it, right? And the idea of getting everybody to take the drug at the same time, in the same way, to follow up and whatnot, the mechanics of that are just overwhelming. So of course, most science doesn't work that way. Rarely ever can you do a census. You can count everybody, then follow them over time. So you do sampling. So you identify a population, the population that has the characteristics that you are interested in. So an A1C level of between 5 and 6%, right on the edge of the cutoff for A1C levels in type 2 diabetes as a marker. Okay? So how do you sample? If you sample the first 100 people that come in your door, that's one sampling mechanism. It's convenient, right? But is that sample going to represent everybody in the population? What about the folks who didn't hear your advertisement? Well, are their characteristics the same as those who did hear about it? And on. You can very quickly imagine where it's unlikely that the first 100 people in your door are going to be representative of every single person that has an A1C level of between 5 and 6%. So randomization means that you identify the population, and then every person in that population has an equal chance of participating in your study. And you approach your recruitment that way. That controls for a lot of the bias that the convenient sampling introduces. You increase the chance that you'll get representation, provided your sample sizes are large enough. But at any rate, the point is that you have to remove sources of bias, and first come, first serve is, of course, a huge source of bias in terms of recruitment into your study. There are other kinds of biases, and so we'll list a few of them, and there's many listed throughout the book. Chapter 2 introduces half a dozen, I think. The other part about an experiment is coming up with appropriate controls. You may be more aware of the idea of control is, for example, when you're doing test of a new drug, you give people what's called a placebo. And the placebo is the same in every ways as the drug, but it lacks the active ingredient. Okay? But control groups are essential because you're doing a sample, and so therefore a lot of things can happen over time. People get better without any intervention at all, which is obviously fantastic, but it isn't the same thing as assigning their getting better to the treatment that you gave them. Okay, so then the other aspect of good experiments is you got to be blind to the treatments that the subjects receive. So single blind means, well, that the subjects themselves don't know what treatment that they received. So that would be the lady in the tea experiment that R.A. Fisher wrote about. She didn't know whether she got milk first or tea first. Double blind means that the person, the medical staff, the doctor, the researcher, whomever who is interacting with the subject doesn't know what treatment they received. Because you can imagine, it's a fairly obvious thing. Look, you've been paid by a pharmaceutical company, we'll say, to test the effectiveness of this new drug treatment, right? So what's the answer that you want to get? You want to be able to show that the treatment works, right? You'd like to continue to do business with the pharmaceutical company. It's your job, right? But the randomization eliminates that source of bias. If you don't know what treatment the subject received, then even though you want a certain outcome, you have no way of intervening short of outright fraud, okay, to manipulate the response in the way that you want. So the results will fall out however they will. And so double-blind, controls, randomization, testable hypotheses, those are characteristics of what we call good experiments. We mentioned this, and this has to do with when you generate your hypotheses. And so classic experiments, you make your hypothesis before you start collecting data. So that's called a priori. Right? But if you make hypotheses after you collect the data, that's called a posteriori. And so that's not to say that if you do this, you make hypotheses after the data is collected, that you're not a scientist. It means that you are falling into a philosophical hole in terms of being able to interpret whether or not the results confirm or refute your hypothesis. The data weren't collected specifically to test that. You didn't design an experiment. You're simply looking for patterns in the data. And so we'll talk a little bit about that, because that approach is now very, very common in business. Collect huge amount of data. I don't know where you get it. Well, every time you do a Google search, data is being generated about your behavior, right? And so Google saves that information, puts it into some algorithms, and then spits out your results and sells your results to advertisers, right? And so they're looking at patterns, though. They're not testing cause and effect. They're not saying that because you looked at, say, the Seattle Times, that necessarily means that you're going to buy a new couch soon, okay? But overall, in the millions of people that look at the Seattle Times, that might correlate with a slight tendency to buy new furniture. So that, even though the individual, it doesn't tell you too much, collectively in the aggregate, that pattern may be there, and so businesses will be willing to advertise. Okay, so what I'm getting at is there's a whole discipline of philosophy that talks about how do we actually know what we know. And so this is called epistemology. That's the field, how knowledge is acquired. And whether you buy into this or not, there certainly are other ways of knowing, but the scientific method is absolutely the best at identifying cause and effect. A critical aspect of doing scientific method, of course, is having good critical thinking skills, right? And so I'm advertising your time with me is we're increasing your statistical thinking muscles, and that of course makes you a better critical thinker. You get some practice in doing that, and homework 1 is your first instance of that practice. I'm asking you to take a look at this word problem and identify the assumptions that the writer makes in order to reach his conclusions. I think it's about football, so it's not the least bit about biology, but at any rate, so critical thinking means you understand sort of that there are facts, and that you understand the concept that evidence accumulates on one side or another in terms of the questions that you're asking, and you have to be aware of the biases that go into the collecting of evidence in facts and interpretation, et cetera, because bias, which is a cognitive thing about how we think and behave, introduces systematic error. So well back in the beginning, in your first chemistry course, in physics and in biology, we talked about random error and systematic error. Random error is things happen simply by chance. There's no, an instrument is only as precise as it can be. There's electronics underneath. The universe is sending gamma rays. Random events happen, so therefore we wouldn't expect a measurement on the same object to be exactly the same over and over and over again. So that's random error. Systematic error, though, is that there's a cause, a reason that you don't get the right answer over and over again. And so that's a bias. So cognitive biases are an important part about how you design and interpret data. Design an experiment, interpret the data that comes from the experiment, right? So confirmation bias. So remember we talked about the researcher who is testing a new drug. He's received money from the pharmaceutical to do this test. So don't you think, even if he's a very honest person, he's got his fingers crossed and he's hoping that there will be a large difference between the control group and the new drug. So if he doesn't double blind in the experiment, it's going to be hard to say that there wasn't what's called confirmation bias. You got the results that you wanted. Okay, so we in science now, for a number of historical events that happen, are required to state up front what our potential conflicts of interest are. Again, thinking about other ways of knowing, not every way of knowing puts up front or advertises, I do receive money from the pharmaceutical company, or I do work for this particular conservation group, et cetera, et cetera. So conflicts of interest is a type of a source of confirmation bias. So we try to remove that first by declaring it, and then second by designing the experiment in a way that you can control for it. Selection bias. You can imagine that when you're recruiting for a pharmaceutical test, that you might not want to have unhealthy people in your study. So you sort of pick and choose who goes into your different groups, and so that means that you can artificially inflate the difference between your groups, and so clearly that's an error. It's not actually testing the effectiveness of the new drug. Hindsight bias. Well, those of us who say, the pandemic was inevitable, that's called hindsight bias. There was nothing inevitable about SARS-CoV-2 in particular. Now, those who were studying, are epidemiologists, and we're looking at viruses coming out of certain places in the world have been predicting for years that there would be a new pandemic, right? But the fact that SARS-CoV-2 has swept the globe over and over again, that's a hindsight bias. It wasn't inevitable that that particular virus was going to do it. And so there's many other kinds of cognitive biases. And so the point being is that experiments, well-designed experiments, help mitigate sources of bias. Okay, so we're going to call it quits. So that was, about an hour and 10 minutes. That's a pretty long slug. So keep working on your assignments, and I'll look for your questions in Canvas. Thank you.